Hi, my name is Joseph Ward. I'm the founder and chief flight instructor here at vHorizon Flight Center. Today I'm going to take you through the slow flight portion of today's ground school material. Okay, here's the deal. What I'm going to do is I'm going to stick you in an airplane that's capable of doing 120 knots. That's twice as fast as most cars on the freeway below. And I have only one request. I want you to fly as slow as you can. This sounds reasonable, right? Well, not really. There is, however, a good reason for flying slowly. The practice of slow flight is providing ground in which you prepare for aviation's biggest event, the landing. After all, you don't want to land at cruise speeds because airplanes weren't designed to maneuver on the surface at high velocities. You don't want to burn the tires off the rims, do you? Just kidding, but it's not far from the truth. In general, the slower you are upon touchdown, the easier it is to control the airplane on the runway. Additionally, airplanes can't fly too slowly or they'll cease flying and start falling. This is called stalling, but it has nothing to do with the engine stopping, as you'll later learn. That's why I want you to feel comfortable operating at slower speeds so you'll know where the dangers are. And, as you'll eventually discover, it's sometimes necessary to follow slower airplanes. You need to know how to adjust your airspeed to prevent chewing up their tail feathers. These are only a few of the reasons we practice slow flight. It's an important maneuver, so let's get started by discussing how airplane wings develop lift. Well, the wing has several distinct parts: the upper cambered surface, the lowered cambered surface, leading edge, trailing edge, and chord line, as shown in this picture. And this picture shows the 5 components of a wing. Notice that the upper cambered, or meaning curved, surface seems to have a greater curve to it than the lower cambered surface. This isn't accidental. In fact, this is so important that we'll talk about it in detail shortly. Perhaps the only term whose definition isn't intuitively obvious is the chord line. The chord line is an imaginary line connecting the wing's leading edge and its trailing edge. Believe me, there is no line inside the wing that looks like this. It's only imaginary. Just like the arrows showing the forces in straight and level flight. The chord line does something similar. Given the wing's curved surfaces, it's difficult to tell which way the wing points. Since engineers don't like uncertainty, they agreed that the chord line will represent the general shape of a wing. Let's talk about how the wing works. To understand lift, you must visualize how the wing attacks the air. Aeronautical engineers talk about the wing contacting or attacking the air at a specific angle. What part of the wing does the attacking? Is it the leading edge, is it the trailing edge, or is it the bottom of the wing? This is where the definition of chord line becomes useful. Because wings come in variable sizes and shapes, it is sometimes difficult to determine exactly how and where the wind strikes the wing. Fortunately, the chord line substitutes as a general reference for the shape of the wing. If I say that the wind blows onto the wing at an 18-degree angle, I'm saying that the angle between the wind and the chord line is 18 degrees, as shown in this picture. This picture shows the angle of attack. The angle of attack is the angle between the chord line and the relative wind. This is the wind that is blowing on the wing. This distinction, although seemingly trite, is as important to an engineer as tightly stitched pant seams are to a matador. Let's talk a little bit about relative wind. Only one more definition needs to be absorbed before the secrets of lift are developed. That term is called the relative wind. Movement of an airplane generates wind over the wing. This wind is called the relative wind because it is relative to, or results from, motion. For instance, in this picture, no matter which way the jogger runs, he feels wind in his face that's relative or opposite and equal to his motion. This picture shows relative wind. The relative wind is wind resulting from an object's motion. Despite the actual wind blowing from behind, the jogger feels wind on his face as a result of his running motion. Relative wind is relative or opposite and equal to the movement of an object. Relative wind is movement generated wind that's equal to and opposite to the motion of the airplane. To illustrate this point, stick your hand out the window of a moving automobile. Keep all of the body parts inside, please. You'll feel wind blowing opposite the motion of the car. Move the airplane forward as shown by airplane A in this picture, and wind blows on its nose. Once again, this picture shows all illustrations how they show relative wind is opposite and equal to the motion of the airplane. As an airplane climbs or ascends, that is, moves up or down the imaginary hill we discussed in turns, relative wind still blows on its nose, as shown by airplanes B and C. But if an airplane drops straight down without a change in pitch, the relative wind blows on its belly, as shown by airplane D. As far as airplane D is concerned, the wind is blowing on its belly despite the level attitude. The important principle to remember is that the relative wind is independent of which way the airplane's nose is pointed. Relative wind is opposite in direction and equal to the airplane's velocity. Let's see how the wing actually attacks the wind and develops lift. Attacking the air. An airplane is unlike a gun and a car in that its vertical climb path is different from its incline, or the direction it points upward. Remember that 750-foot tower off the end of the runway? On takeoff, if you point your airplane slightly above the top of that obstacle, like a rifle sight, it's unlikely that you're going to clear it. Remember, airplanes with limited thrust have shallower climb paths, unlike some fighter jets. The most important principle to understand here is that the nose, therefore the wing, can be pointed on an incline that's different from the actual climb path. An angle exists between the amount the wing is inclined and its climb path, and you'll soon see why. Remembering that the relative wind is always equal and opposite to the flight path, it's more precise to say that an angle exists between the chord line and the relative wind. This angle is known as the angle of attack, as shown in this picture. And once again, this picture shows the angle of attack. This picture shows the wing, or chord line, of airplane A making a 5-degree angle to the relative wind. And this picture shows the angle of attack and how lift develops. A more common way of saying this is that the wing's angle of attack is 5 degrees. Airplanes B, C, and D show increasing angle of attacks of 10 degrees, 30 degrees, and 45 degrees respectively. The greater the difference between the wing and the relative wind, the greater the angle of attack. And as you're about to see, the wing's lift is directly associated with its angle of attack. Let's talk about how lift develops. The wing is the ultimate air slicer. As powerful as any samurai sword or karate chop, it's a precision device for slicing air in this specific way. Wings are expressly built to plow through air molecules, separating them either above or below while offering little resistance in the horizontal direction. Any horizontal resistance slows the wing down. This horizontal resistance is called drag, and it's definitely a case of less being better. This picture shows how the airfoil, or a fancy name for a wing, splits the wind when it's at a 10-degree angle of attack. This picture shows the airfoil flow over and under a wing. Lift from an airfoil is produced by air flowing over and under the wing. Airflow strikes the leading edge of the wind, forcing some air over and some under the airfoil. Both the air flowing over and the air flowing under the wing are responsible for generating lift. Let's first examine how the airflow striking the bottom of the wing produces some of the total lift that is developed. Let's talk about impact versus pressure lift. Sticking your hand out the window of a moving automobile does two things. It demonstrates how a relatively flat surface develops lift, and it signals a left turn. This picture shows how wind is deflected downward when it strikes your hand. And this picture shows impact lift. Airflow striking the hand is deflected downward. This imparts an equal and opposite upward force to the hand. High pressure is created on the bottom of the hand by impacting air molecules. According to Sir Isaac Newton, who knew about such things, for every action there is an equal and opposite reaction. Wind deflected downward by the airfoil creates an upward and opposite movement of the wing. This upward movement is caused by the impact energy of billions of tiny air molecules striking the underside of the wing. Also, higher pressure on the bottom surface of the wing results from this molecular impact. The wing moves upward as if it were being pushed from below. This type of lift is known as barn door lift or impact lift. It generally contributes only a small portion of the total lift produced by the wings, which means that man and women do not fly by barn door lift alone. A more subtle and powerful form of lift occurs from curved airflow over the top of the wing. Bending the wind with the wing. Airliners, indeed all airplanes, bend something else. They use their wings to bend the wind. Wind bending did not sound sophisticated enough to explain why airplanes fly, so it was given a fancy Greek title. We call wind bending aerodynamics. Simply stated, the wing is a precision device for bending or curving the wind downward. But how does bending the wind over the wing create lift? Let's find out. This picture shows a cross-section of an airfoil. This picture shows the airflow above and below the wing at a small angle of attack. At low angles of attack, the air above the wing is curved while the air below the wing is relatively straight. Examine its shape carefully. At small angles of attack, the air flowing above the wing is bent or curved with great precision as it follows the upper cambered surface. A rather straight surface on the bottom of the wing leaves the air underneath relatively unbent. Bending or curving the wind above the wing forces air to travel a greater distance than the straighter airflow below. If the wind above is to reach the trailing edge at nearly the same time as the wind below, science and experiments say that it does, it must speed up to cover the greater distance. For example, assume you are walking your pit bull terrier named Bob on a leash. You are on the sidewalk and Bob is walking in the gutter, as shown in this picture. This picture shows the different distances in curvature above than below the car. Also has a wing too. Bob encounters a parked Volkswagen and decides to walk over the car rather than around it. Obviously, the distance over the car is greater than the distance you will travel on the sidewalk. In order for Bob to avoid being choked by a leash, he will have to speed up slightly as he covers this greater distance. Do you notice the resemblance of the VW's profile to a wing? It's curved on top and rather straight on the bottom. As air flows over the wing, it curves and speeds up. Let's talk about something else here. Thanks for the lift, Monsieur Bernoulli. Something remarkable happens when air flowing over a surface increases its speed. In the late 1600s, a Swiss physicist named Jacob Bernoulli figured out that the faster air flows over a surface, the less pressure it exerts on that surface. High velocity airflow over a wing causes a slight decrease in pressure on the wing's upper surface. In other words, the pressure on top of the wing is now less than the pressure on the bottom of the wing. Known as Bernoulli's principle, this wonderful trick is what keeps airplanes from being large, inexpensive doorstops. Most wings are designed with their upper surface curved and their lower surface relatively straight. Because of the wing's shape, even at a small angle of attack, a cambered wing still adds a slight curve and acceleration to the wind. This produces the lift you learn to love, particularly if you think of an airplane should fly. Angle of attack and the generation of lift. During takeoff on a commercial airliner, have you ever noticed that the pilot always raises the nose slightly to begin the climb after attaining a minimum forward speed? This is called rotation. As the airplane accelerates for takeoff, it eventually reaches a sufficient speed to begin flying. At this relatively slow speed, however, the wing's engineered curve isn't capable of curving or deflecting enough air downward to produce the necessary lift for flight. This is why the airplane doesn't hop off the ground like a grasshopper that just landed on a hot barbecue. The pilot must do something extra to add an additional curve to the wind. Raising the nose slightly increases the angle of attack. This forces the air to undergo an additional curve greater than that which the engineered shape of the airfoil can produce. This picture depicts the process. And this picture shows two forms of lift. A, the lift from low pressure at large angles of attack. The airflow is forced to curve beyond the engineered shape of the wing. And B, impact lift on the bottom of the wing increases at a high angle of attack. With this additional curvature, air travels a greater distance, its speed increases, pressure lowers on top of the airfoil, and sufficient lift to begin flying is produced at a slower airspeed. Thanks for the lift, Bernoulli. Greater impact lift results from increased exposure of the wing's lower surface to the relative wind. The result is that an increasing angle of attack permits the airplane to produce the necessary lift for flight at slower airspeed. Now you know how airfoils generate the required lift at slower airspeeds. You also know why airplanes take off and land at slower speeds seem to have a rather nose-high attitude. But what happens at higher airspeeds? Have you noticed that in cruise flight at cruise airspeeds, airplanes fly at a near level flight attitudes? This picture shows an airplane at several different angles of attack. This picture shows the relationship between angle of attack and speed. With speed variations in level of flight, the relationship between the angle of attack and airspeed is clearly shown. With increasing airspeed, the airplane requires a smaller angle of attack to remain airborne. As the airplane's airspeed decreases, a larger angle of attack is necessary. At higher speeds, airplanes can fly at lower angles of attack because the wing's shape generates sufficient lift. Slow the airplane, and the wing must artificially bend the wind by increasing its angle of attack. An intimate and sizzling relationship exists between angle of attack and lift. At small angles of attack, such as during cruise flight, the engineered shape of the airfoil generates sufficient lift for flight as long as the airspeed is high. The impact of air underneath the wing doesn't play as big a role in lift development at higher or cruise speeds because less of the wing's underside is exposed to the wind. In summary, the slower an airplane moves, the greater the angle of attack needed for flight. There is, however, such a thing as too much of a good thing. Bend the air too much, and instead of the air flowing smoothly over the wing and increasing lift, it bubbles and burbles and pretty much fails to be uplifting. We call this condition a stall, and this will be covered in a future class. Now it's time to talk about the details of entering and leaving slow flight as it's done in the air.